everyone, welcome back to Math 256. This is Scott. Let's get started. What we are going to be doing now is our one and only foray into Chapter 5. So we're going to talk about Section 5.1, which has to do with linearization. Okay, so let's recall what we know about systems. So we're going back to systems. So recall. If we have an autonomous linear system, an autonomous linear homogeneous system of the form, and the default format for something like this would be something like x prime equals ax plus by, y prime equals cx plus dy. So notice that both of these are linear in x and y, and there's no constant term. That's the important thing. So that's what's at stake in the systems that we've looked at so far. So if we have a system of this form, then we can use the matrix A, which is made up of just these coefficients, A, B, C, and D, and its eigenvalues to classify the equilibrium at the origin. And in particular, we know very well what the categorization falls into. It just falls into the various determinations that, for example, the trace determinant plane could give us. But let's remember what those categories are. So possibilities. So first big heading is two distinct real eigenvalues. And if you remember, we broke those down into both positive, both negative, or one each. Both positive was a source, both negative was a sink, and one positive, one negative that was a saddle point. Okay, we remember that. Case 2, complex. complex eigenvalues. And here we had something that involved some sort of rotation, either spiral, inward slash outward, or else a center. So that's a positive real part. That was a spiral source. Negative real part. That's a spiral sink. And then real part equals 0. In other words, it's purely imaginary. That represented a center. All right. And then the third possibility that we discovered, or that we explored, was repeated. Repeated real eigenvalues. And we had two possibilities there. If it was defective, we have an improper source slash sink. And if it was complete, a proper source slash sink. Okay, so that's pretty much what we have as far as our possibilities. But what if the eigenvalue is 0? That's not covered by any of these cases. What if lambda equals 0? Is an eigenvalue. Well, we're not going to really delve into too much of the ins and outs of this particular case, because then we have to consider, is it repeated, is it not repeated, etc. The important thing to note is what that would mean about the corresponding piece of the solution. So let's say that V is an associated eigenvector. Is an associated eigenvector for lambda equals 0. Then think about the solution x equals just e to the lambda t times v will just be equal, or I'll say c lambda t times v. That's just going to be equal to cv. And this represents essentially just something that is a position that is not changing over time. So what this represents is a constant. So this means the weight on V is constant. Meaning that the solution curves will be shifted a fixed amount by this vector, leading to parallel line. Parallel line solutions. And in particular here, let's say something like this. And this is, let's say, direction of v. And this will all be based on whether the other eigenvalue is positive or negative. This represents other eigenvalue is negative, and this represents the case where the other eigenvalue is positive. And again, we don't want to delve too much necessarily into the nitty-gritty of this. That's not our concern, but what is our concern is the takeaway of this, which is that the origin would no longer be what is called an isolated singularity, or an isolated equilibrium. So then, the origin would not be an isolated equilibrium. So basically, the equilibrium points would lie not just at the origin, but they would lie all along the line determined by the direction of v. So each point along this line would be an equally valid equilibrium. So that's not something we've really seen before. So it's an interesting exception to the cases that we've looked at. But that is just by way of preamble for something that we're going to discuss now, which is an extension of the same classification scheme, but for nonlinear systems. So now, our new problem. What about nonlinear systems? So we can't make the same matrices, and so we can't use the same techniques to discuss circumstances that are not linear as we could with systems that were linear. And to get us started on this, let's just have some examples, and then we'll figure out what to do, and then we'll do it to those examples, and then we'll look at the Bluffton view of the situation. So examples. So some examples. All right, so what makes a system non-linear? Well, let's just say A. Let's just say we have a system like this. X prime, y prime is equal to, say, 2x, sorry, it's not the example, x minus 2y minus 8. And then x plus 4y plus 10. So this does not fall into our usual heading because of the presence of these constant terms at the end here. The minus 8, the plus 10. We can't make a coefficient matrix out of this because now we don't even have the regular situation that we typically have. So this is not linear because of the -8 and the +10. Let's have another one like that. X prime is equal to x plus y minus 7. Y prime equals 3x minus y minus 5. Again, same issue. We haven't studied what to do about things like this. Now let's up the ante a little bit and start making the equations more flagrantly nonlinear. X prime equals y minus 1, y prime equals x squared minus 1. Now let's go even further. X prime equals xy minus 2. Y prime equals x minus 2y. So what makes these cases nonlinear is not only the presence of the constants, but then also the more complicated expressions that are wrapped up in the x prime and the y prime. And then finally, for our last example, let's look at the competing species model that we looked at when we were studying null climbs and that sort of thing. In which we already found the equilibria, and we did some sketching of things, but let's now look at it from a new perspective. So this is the equation x prime equals x times 1 minus x minus 1/3 xy. Y prime equals y times 1 minus y minus 1/3 xy. So we've already actually looked at this situation from the perspective of the phase plane and making the null climbs and everything like that. Now here we're going to approach all of these cases by the same basic approach. So our tool. And this tool is linearization. Okay, so the basic idea of linearization is that when we are next to an equilibrium for these systems, and we'll have to find these equilibria, we're going to have to work for them. They're not going to be just for free by default at the origin anymore. These are going to be equilibria that we are going to have to find. But when we have found the equilibria, we can actually approximate our system by a linear system to get the behavior near those equilibria. So when we have found the equilibria of these systems, and you find this, by setting x prime and y prime to 0, and finding all the combinations that satisfy this system of equations. So when we have found the equilibria of these systems, then we can approximate the original system by a linear system centered. So at that point, I should say at each of those points. At each of those points. And the way this works is through a tool called the Jacobian matrix. The linear system that approximates the original nonlinear system is the one whose coefficient matrix is generated by and we can call it J fx fy gx gy where x prime equals f of x, f of xy, y prime equals g of xy. Oops, sorry. There, now you can see what I'm writing. And fx, fy, gx, and gy represent the partial derivatives of f and g with respect to each of the variables. Now, a reminder, in case you haven't really explored partial derivatives that much, so remember, we looked at this a little bit here and there, but let's just be clear. To take a partial derivative with respect to one variable treat any other variables, here we only have two variables, so there's just one other variable, as constants. Now, this may seem very strange. This may seem like a very strange process, taking these partial derivatives and such, but let's just think about what derivatives even mean. They represent the rate of change. A partial derivative represents the rate of change in a specific direction, the x direction or the y direction. And so, if we want to approximate a system that isn't already linear by a linear system, we need rates of change in each direction. And what better way to get the rate of change than to calculate the partial derivative? So all in all, the process here, when you untangle what the pieces are each representing, hopefully can be something that you can make some sense of. But now let's make our formal procedure completely set. So here's our procedure. So our procedure. So step one. Step one is to find the equilibrium points. Step two. Calculate the partial derivatives fx, fy, gx, gy. To make the Jacobian matrix. Now, step three. Plug in the coordinates of each equilibrium point to get a numerical matrix. So you'll have a value for x, a value for y, so you can just get a matrix that has just numbers in it. Step four. Find the eigenvalues. Of this matrix. If lambda equals 0, is an eigenvalue, then the point is not an isolated equilibrium, and we would just stop there. But if the eigenvalues are all non-zero, then we can basically use the same classification scheme that we have been using for linear systems at the origin to classify the equilibrium points. So step 5, if lambda is not equal to 0, or I should say if 0 is not an equilibrium, or not an eigenvalue, or non-zero, then we can use the same classification scheme for these equilibria equilibrium points. As we used above for linear systems. Centered at the origin. All right, so that is our 5-point plan for analyzing the equilibria of these no longer assumed to be linear systems. Let's actually try this out. So let's give this a go. We'll go example by example. We'll find their equilibria, and then we will classify those equilibrium points. So examples. So here are the instructions. Find and classify the equilibrium points of the following systems. Then confirm. Confirm your classifications with technology. And by technology here, what I really mean is a direction field such as Bluffton, i.e. Bluffton. All right, so let's look at our examples one by one. So A. So here, x prime equals x minus 2y minus 8. Y prime equals x plus 4y plus 10. Okay, so right now we have a system that is not linear because it has these constant terms on it. But let's just find out what the equilibrium point is, and we'll just follow our 5-step plan here and see what we get. Okay, so first we need to find the equilibrium points. So So 0 equals x minus 2y minus 8, and 0 equals x plus 4y plus 10. All right, well, to solve this, this system of two equations in two unknowns, what I can just do is substitution would be a perfectly reasonable thing to do. Other things that would be reasonable would be to use any kind of algebra, like linear algebraic technique, such as turn this into a correct form and make an augmented matrix out of it. So you could move the constants over and you could have an augmented matrix, and you could use all of your fancy linear algebra know-how from there. But this is a relatively innocent looking equation, so let's just solve it by substitution. So I will just solve this one for x, and I'll just plug that in for x over here. It's sometimes the easiest way is just power forward, not worry about the fanciest techniques you know, just make the most out of some very straightforward algebra. Just solve for one variable, plug it into the other equation, see what you get. So 0 equals 2y plus 8 plus 4y, so it's going to be 6y plus 18. So then if I subtract 18 divided by 6, I get y equals negative 3. If I take that and I plug that back up here, I'll get x equals negative 3 times 2 is negative 6, plus 8 is 2. So there's only one equilibrium, and that's at 2, negative 3. By the way, this system is sometimes called almost linear because it's only nonlinear due to those constant terms. And when you have a system that is almost linear, you will frequently find it to be the case that you will end up with just a single equilibrium point. So the origin basically just gets displaced. Okay. Now, f of x comma y equals x minus 2y minus 8. Just identifying the players in this little drama. G of xy is equal to x plus 4y plus 10. So now I can just calculate my partial derivatives. So as I take the derivative with respect to x here, I'm treating y the same way I would treat like the number 5 or pi or something like that, any constant. So when I take the derivative with respect to x, this is just going to be 1. As I take the derivative with respect to y, so it's going to be 1 plus 0 plus 0. If I take the derivative with respect to y, it's going to be 0 minus 2 plus 0. And it's not a coincidence here that in this almost linear equation, the fx and the fy match the coefficients of the x and the y. G of x here is going to equal just 1 plus 0 plus 0. Gy is going to equal 0 plus 4 plus 0. So then J, remember it's FFGG. So sometimes it can be a little bit hard to remember some of these various matrices that are made, especially the more you learn, because there are a lot of different variations on these types of matrices. There's the Wronskian, which we saw during the variation of parameters. If you've taken vector calculus, you may be familiar with the Hessian, which is a different matrix that is made of a different combination of derivatives. But the Jacobian here, one easy way to remember it is that in the case of these almost linear equations, it actually literally is the coefficients going here, 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 and here. So this is actually just going to be constantly equal to 1, negative 2, 1, and 4. So notice that this is not dependent on x and y, and that'll be the case generally for the Jacobians of these almost linear systems. So now here, actually, I can change my script a little bit if I want to. I can depart from it, and instead of finding the eigenvalues, I can worry about the trace and the determinant. However, let's just stick with our usual plan. So then the determinant of 1 minus lambda, negative 2, 1, 4 minus lambda. So remember, this is the usual way we find eigenvalues. And we're not even going to have to find any eigenvectors here, so it's nice and relaxing. 1 minus lambda, 4 minus lambda, plus 2 equals 0, lambda squared, minus 4 lambda plus 1 lambda is going to be minus 3 lambda, plus 4 plus 2, and so that's going to be plus 6, and so I had a little bit of a misgiving about that, and that's because, of course, as you were all screaming at your computers, that is actually minus 5. So it's minus 4, minus 4, minus 1, minus 5. Okay, so then that's going to be lambda minus 3, lambda minus 2 equals 0, meaning lambda equals 3 and 2, both positive, both real, so this is going to be a source at 2 comma negative 3. And we'll confirm this with Bluffton when we'll just confirm all of them with Bluffton at once rather than flip back and forth between them. Okay, so that's how this goes for an almost linear system such as this. Now let's look at example B, which is also almost linear, and so we should expect it to go down a very similar line. So example B, we had x prime equals x plus y minus 7. Y prime is equal to 3x minus y minus 5. So step 1, and actually, better yet, let's not even worry about setting up step 1, step 2, step 3, because I'm not going to remember to do it consistently, so why set myself up for that by making it look like that's what I'm going to do. Okay, so 0 equals x plus y minus 7, and 0 equals 3x minus y minus 5. So those would be our two equations here. And to solve them, we can just do what we did before here, just because I'm thinking ahead a little bit, I don't want to have to distribute something. So I might as well just solve this one for y, and I'll get negative x plus 7. And that goes in here. So then 0 equals 3x plus x minus 7 minus 5. So 0 equals 4x minus 12, which then add 12 divided by 4 gives us x equals 3. And then for the other one here, I'm sorry, it was source at 2 from the negative 3 and the previous one. And then you take that and you plug it in here, and it's going to be negative 3 plus 7 is going to be 4. So 3, 4. Okay, well then, now let's just define what our f and our g are. Fxy is equal to x plus y minus 7. Gxy is 3x minus y minus 5. And so then f sub x, so the partial derivative of f with respect to x, is going to be 1 plus 0 plus 0. G sub x will be 3. 0, 0. F sub y will be 0 plus 1 plus 0. And g sub y will be 0 minus 1 minus 0. So j, which is equal to f, f, g, g. Here, once again, oops, I don't actually have any x's or y's left in here. This almost linear equation does not produce that sort of thing, so I don't have to change anything here. And so then I will just find the equilibria, or sorry, find the eigenvalues of the usual means. And again, I could just use the trace determinant plane on this. It would be perfectly reasonable and common to do so. All right, so then what do we have? Lambda squared. Might save us a mistake anyway. Okay, so what do we have here? We have lambda squared, we have positive lambda minus lambda, so those disappear. Minus 1 minus 3 equals 0. So lambda squared minus 4 equals 0. Lambda, we can see then is going to equal positive or negative 2, which means that 3 comma 4 is a saddle point. Okay, so that's what we say about B. We'll let Bluffton see if we're right or not. Now, for something that is a little bit less linear. So those first two were both almost linear. Let's see what happens in a case like C here. So x prime equals y minus 1. Y prime is equal to x squared minus 1. So now, first off, set everything equal to 0. So 0 equals y minus 1, and 0 equals x squared minus 1. And once again here, now that we're extra unlinear, don't go around using the techniques of linear algebra really. Instead, just solve and substitute. So here y equals 1. Good to know. Here, there's no y to plug in, so what we have is x squared equals 1, so x equals plus or minus 1. And so then that's going to give us 2 equilibrium points for each combination here. 1, 1, and negative 1, 1. Are the equilibrium. All right, well now if f is equal to y minus 1 and g is equal to x squared minus 1, then fx is going to be the derivative of this with respect to x, but with respect to x, there is no x, and so it's going to be 0. Fy is going to equal 1. Okay. Here, g sub x is going to be 2x, and g sub y is going to equal 0. So that means that j is going to equal 0, 1, 2x, and 0. So that's our Jacobian matrix. And now what we will do is look to the eigenvalues at each of these points. So let's start with 1, 1. So j of 1, 1 is the effect of putting 1 for x and 1 for y. So the pieces of this that were constant will just be what they were. And so we'll have 0, 1, 2, 0. Which then, if we put in the lambdas, take the determinant, set it equal to 0, we're going to have lambda squared minus 2 equals 0, which means lambda is going to equal plus or minus square root of 2, which makes it a saddle point. Now if we try the same thing with negative 1 comma 0, sorry, negative 1 comma 1, I mean, negative 1 comma 1, then that means x is going to be negative 1, y is going to be 1. That's going to equal 0, 1. It's going to now be negative 2 and 0. And 0 minus lambda, 1, negative 2, 0 minus lambda. The determinant of that, set it equal to 0. It's going to be lambda squared. And then plus 2 equals 0, which is going to give us lambda squared equals negative 2, which means that lambda is going to equal plus or minus root 2i, which is a case of a complex conjugate pair of eigenvalues which have 0 for their real part, and so this represents a center. Now, once again, we're only talking about near this point. It will look like a center. As it's farther away from this point, it may look, it may spiral inward, outward. It can do a lot of different things here. All right. Now, another case. Let's take one that's also nonlinear here. We'll go xy minus 2 and y prime equals x minus 2y. So now set it equal to 0, and I have xy minus 2 equals 0, and I have 0 equals x minus 2y. So I think I might try my luck with solving this second one first. I'll solve x equals 2y. I'll plug that in over here, and I'll get 2y times y minus 2. And then that means I'm going to have 0 equals 2y squared minus 2. So in other words, if I add 2, divide by 2, I'll have y squared equals 1. Y equals plus or minus 1. So then So then if y equals 1 or -1, we'll get the corresponding x over here. So then we'll have x equals positive and -2, and those will be positive and -2 to match the y's. So we'll have 2, 1, and -2, -1 for our equilibrium points. Now we will cast the roles for the Jacobian play. So f equals xy minus 2, g equals x minus 2y. So then f sub x is equal to. Now here's where it gets where people sometimes get a little confused when it comes to taking partial derivatives when you have these types of terms. Remember that when we're taking the partial derivative of x with respect, or partial derivative with respect to x, we are treating y the same way we would treat a constant like for example pi or 5. If this had said 5x, then the derivative of it would be just 5. Oops. If it had said pi x, the derivative of it would just be pi. So in other words, the derivative here is y. Similarly, the derivative on this one is just x. Here we have no surprises. This one is just a linear function, in fact, so g sub x is going to be 1, g sub y is going to be -2. Which means that our Jacobian matrix is going to equal y, x, 1, -2. So now we'll just take it piece by piece. So j of 2, 1. That's 2 for x, 1 for y. That means 1, 2, 1, -2. Now we almost here ended up with 2 linearly dependent pieces, and in that case, that would mean that 0 was an eigenvalue, which would mean that we were talking about a point that was not isolated. But that didn't quite happen, so here we go. So then 1 minus lambda, 2, 1, -2 minus lambda. Set that equal to 0. 1 minus lambda, -2 minus lambda, minus 2 equals 0. It's going to be lambda squared. We're going to have plus 2 lambda plus lambda, it's going to be plus 3 lambda, minus 2 minus 2, it's going to be minus 4, equals 0. All right, now can we factor this? It looks like we can. We can do lambda plus 4 times lambda minus 1 equals 0. Lambda equals -4 and 1, which is going to be a saddle point. Similarly, we should say at 2, 1. Similarly, if we put in the other equilibrium, in fact, actually at all of these, you should go back and specify, just to be extra clear here, at 1, 1, at -1, 1, for the specific points that have behaviors that we've found. Okay. So back to the main program here. So the Jacobian, once again, was y x 1, -2. It's going to be -1, -2, 1, -2. And again, we were playing with fire here for a second. It looked like we might have been making a matrix that was that had two linearly dependent rows, and such a matrix would then have a determinant of 0, which would mean that one of its eigenvalues was 0. So that we narrowly escaped that fate, but it's something to always look out for. And we would have discovered that when we got to this point anyway. So what do we have? We have -1 minus lambda, -2 minus lambda, plus 2 equals 0. And so it's going to be lambda squared, +2 lambda, plus 3 lambda is going to be. And now here we have +2, +2. And so that means we're going to have a total of +4 equals 0. Now this one, unlike the previous one, is not factorable. So let's just go to the quadratic formula here. A equals 1, B equals 3, C equals 4, meaning lambda equals -3 plus or minus the square root of B squared minus 4AC divided by 2A. -3 plus or minus, looks like that is square root of -7, so that's going to be √7I, and I might as well just divide by 2 on both of these pieces. And the important thing is that it is complex and that its real part is 0. So it looks like we have a spiral sink at -2, -1. Okay, so those were some warm-ups, and now the competing species model, which, if you remember, we actually already found all the equilibrium points of this by looking at the null lines and finding their intersection and such. But let's take this from the top, doing it this new way. So the competing species model had x prime is equal to x times 1 minus x minus 1/3 xy, y prime equals y times 1 minus y minus 1/3 xy. And if you remember what this means, it's two species that in isolation would just have a logistic growth model, but which are negatively impacted by their interactions with the other species, but weakly so. This number here determines whether the interactions are weak or strong. So these species, although in competition, are weakly in competition. But let's just let the math speak for itself. So 0 equals x times 1 minus x minus 1/3 xy, and 0 equals y times 1 minus y minus 1/3 xy. Alright, well, you may be tempted to FOIL or to distribute these things out, but that's not going to really help us on them. It's actually going to be kind of counterproductive. It'll be a little better if we move this over to here. And by the same token, we'll move this one over to here, and we'll just see where that gets us. All right, well, right here we can notice that if x is equal to 0, that would be a solution. And if it's not, then we can divide by it, and that'll take us to the case 1/3 y equals 1 minus x. Over here, by the same token, y equals 0, or 1/3 x equals 1 minus y. So these correspond actually basically to the nullclines that we have already been looking at. Let's just oops, 3 minus 3x, and here just to get these fractions out of our way, let's just go ahead and put that in there. Okay, so then let's just put these into combination. X equals 0, y equals 0. 0, 0. X equals 0, x equals 3 minus 3y. This implies that that 0 equals 3 minus 3y, which implies that 3y equals 3, which implies that y equals 1. So that leads us to, this is case 1, case 2. So this one leads us to the case 0, 1. Next case. So y equals 3 minus 3x, and y equals 0. So that leads then to 0 equals 3 minus 3x, which would lead to 3x equals 3, so x equals 1. That would lead to the case of 1 for x, 0 for y. And then finally here we will have the case where y equals 3 minus 3x and x equals 3 minus 3y. So let's just go ahead and put that into here. And see where that gets us. So y equals 3 minus 9 plus 9y. So if I subtract 9y from both sides, I'll have negative 8y equals negative 6. So that means y equals 3/4. And if I put that into the other equation, so x equals 3 minus 3 times 3/4. So what is that? That's 12/4 minus 9/4 equals 3/4. So that's going to lead us to 3/4, 3/4. Which, if you take a trip on the Wayback Machine and look back at whenever we dealt with these cases before, whenever we found the equilibria of this system, that is again what we found way back then. What we did there was just setting the nullclines each equal to each other, and that's effectively what we just did here again. So same process fundamentally. Okay, now what is f? What is y? Or sorry, what is f? What is g in this case? So f is equal to x times 1 minus x This is what we need in order to find the Jacobian. Minus 1/3 xy. Now I think it will be to our advantage to multiply this out. So this is going to be x minus x squared minus 1/3 xy. G is very similar. Y times 1 minus y minus 1/3 xy. So these equations are basically symmetrical in x and y. But let's see here. Then it's going to give us y minus y squared minus 1/3 xy. And so then when we want to find the Jacobian, we'll need to find some partial derivatives. So taking the partial derivative of this with respect to x, it's going to be derivative with respect to x is 1 minus 2x minus 1/3 y. Remember, we're treating y basically like it's a coefficient of x here. And f sub y will be nothing minus nothing minus 1/3 x. Similarly here, g sub x is going to be nothing minus nothing minus 1/3 y. And g sub y is going to be 1 minus 2y this time, minus 1/3 x. All right, well now let's go ahead and find our Jacobians. So j sub xy is going to be 1 minus 2x minus 1/3 y, negative 1/3 y. Here it's going to be negative 1/3 x, and then 1 minus 2y minus 1/3 x. So let's put in point after point here. 0, 0. So 0, 0. So it's 0 for x, 0 for y. So it looks like it's going to be 1, 0, 0, 1, which may strike you as a peculiar solution, because, or peculiar matrix, because it happens to be the identity. Is this a coincidence? Not really. It's not really a coincidence or anything, but the important thing here is that this is going to be one of the very rare cases where we're going to get a repeated lambda of 1, where it actually will be complete. 1 minus lambda, 0, 0, 1 minus lambda equals 0. So 1 minus lambda squared equals 0. So lambda equals 1, multiplicity 1. And this actually is not defective, or multiplicity 2, I mean. This is not defective, because if you look at it, this is going to be, so let's call it a minus lambda I is going to equal 0, 0, 0, 0, which means then I can have two different eigenvectors that satisfy this. For example, v1 could be 1, 0, v2 could be 0, 1, for example. So this is complete. which means we have a proper source at 0, 0. So what that means is actually it's like a star point. So this is not an outcome that we saw very often when we were just talking about linear systems, because we wouldn't usually construct a linear system such as this. It would be totally uncoupled. But according to the approximations that we do when we are turning a system that is not linear into a linear one, that can happen. Okay. Now let's take situation 2, 0, 1. So 0 for x, 1 for y. So what's that going to give us? So it's going to be 1 minus 1/3, negative 1/3, 0, and 1 minus 2. So I'm just going to put that in there so that I don't make any mistakes, or I make the minimum number of mistakes. Negative 1/3, 0, negative 1. All right. So here, I might as well just go ahead and instead of finding the determinant, maybe I'll just go with the trace determinant, instead of finding the eigenvalues, maybe I'll just go with the trace determinant plane. So the trace here is equal to negative 1 plus 2/3. It's going to be negative 1/3. And then the determinant here is going to equal negative 2/3 minus 0, or plus 0. So we're talking about negative, negative for the trace and determinant, and that's going to lead us into a saddle point. Basically, just a negative determinant in general is going to lead to a saddle point because it means that the two eigenvalues must have opposite signs. Now, based on that and the fact that our equations are totally symmetrical in x and y, I have a theory about the point 1, 0, but let's just find out. So 1, 0. So the Jacobian of 1, 0, so it's 1 for x, 0 for y. It's going to equal 1 minus 2 minus 0, 0, negative 1/3, and then over here, 1 minus 1/3. Negative 1, 0, negative 1/3, 2/3. So here it looks like our trace now is going to still be the same, and our determinant is still going to be negative 2/3, which puts us down here on the trace determinant plane, which means that we have a saddle point. All right, and then the final equilibrium here is at the 3/4 point. 3/4. All right, so the Jacobian of this is going to be 1 minus 2 times 3/4. We'll just let the math work itself out here. Minus 1/3 3/4. Negative 1/3 3/4. Down here, negative 1/3 3/4. And over here, 1 minus 2 times 3/4. Minus 1/3 3/4. Now let's actually calculate this. So this is 1 minus, this would be 6/4, or in other words, 1.5. So it's at negative 1/2 minus 1/4, so that'd be negative 3/4. Over here, we're going to have negative 1/4. Over here, we're going to have negative 1/4. And over here, we're going to have, just as before, so it's going to be 1 minus 6/4 is going to be 1 minus 3/2, so it's negative 1/2, just making sure that we weren't wrong the first time. And so we have negative 3/4 here. All right, well, if this is our Jacobian, then let's worry about our eigenvalues. So if we wanted to do the trace and determinant situation, let's see what we would get. So t is going to equal negative, so 3/4 3/4 is 3/2, negative 3/2. And the determinant is going to be 9/16 minus 1/16 is equal to 8/16, which is equal to positive 1/2. So the determinant equals positive 1/2, the trace equals negative 3/2. So now we are in a situation here where we just have to figure out where we are vis-a-vis the parabola. So the parabola, you will recall, occurs at the d equals 1/4 t squared mark. So let's just draw on the parabola. Remember, this is the determinant, this is the trace. And so d equals 1/4 t squared. That is the cutoff point for the various scenarios. So what is 1/4 t squared? It's going to equal 1/4 times 9/4, which equals 9. Now we can see clearly that d is below 9. And so what that means is that we are going to be talking about two real eigenvalues, and because the trace is negative, that means we're over here. So our determinant is well below this this mark, and so we sorry, that's 9/16. What am I saying? 9/16. It's not well below. It's barely below. Barely below. So we're just barely below this mark, and so that means what we have are two distinct real eigenvalues, and because they're over here, they're both negative, so this means that we have a sink. A sink at 3/4 3/4. Which, in the context of the population model of these two species, hopefully will be sensible, because what is going on with these two species, if you recall, is that we found that for values of beta that fit this particular this particular profile, we have a stable equilibrium there. If beta were above 1, it would be unstable, and so we would expect there to be a source. But in this case, we found already through our analysis with null clones and such that this would be in fact stable, i.e. a sink. So those are our various findings for these 5 different examples, and now we'll switch over to Bluffton and get confirmation on what we have seen. All right, so here we are at our typical starting place. Just type Bluffton differential equations into some sort of search engine and search. Systems are what we're talking about here. All right, so let's start with example A, which was x minus 2y minus 8 for the first function. And then x plus 4y plus 10 for the second one. We will get rid of this, which doesn't have any relevance to us. And if you will recall our findings, for example, A, we found that there was an equilibrium at 2, -3, and that it had and that it was a source. So okay, need to zoom out a little bit. I don't need all these negative x values. And so go to here, and I want more negative y values. Let's go -6 to 0. Okay. So 2, -3. Do we have a source here? So it would seem. Now, this one has definitely a look more like it looks like it could almost be a multiplicity 1. I mean a multiplicity 2 eigenvalue, even though we know that we found actually 2 distinct ones, 2 distinct real ones. The reason why it has this appearance is that our 2 eigenvalues are close to each other. And the closer the 2 eigenvalues are to each other, the more the solution will resemble an improper node that you'd get from a multiplicity 2 eigenvalue. So close together eigenvalues produce things that are very similar to repeated eigenvalues. It's just part of the continuity of the situation. So our eigenvalues were 3 and 2. So by being close together, it made it seem very close to being multiplicity 2. All right, let's okay, confirmed on example A. Now let's look at example B. X plus y minus 7 for the first one. And here, let me clear all these curves too while I'm at it. And then over here for the y, we have 3x minus y minus 5. And what we found here was an equilibrium at 3, 4 for the x and the y. So I'm going to make this go from 0 to 6 for x. And I'm going to make y go from 0 to 8, so that we have the equilibrium squarely in the middle of our field of view. And our finding was that it was a saddle point. And sure enough, this is what a saddle point looks like. By the way, the reason for the name is that if you were looking at a 3D graph whose contour lines looked like this, it would resemble a saddle, like for a horse. But once again, example B, picture confirms it. We have indeed at the point 3, 4, a saddle point. All right, now example C. Here what we had was clear these curves. We had y minus 1 for the x prime. We had x squared minus 1 for the y prime. And our equilibrium values were at 1, 1 and negative 1, 1. So I'm going to make my x go from -3 to 3. Seems like a nice spread of the x's. And our y's just have to include 1 and -1, or sorry, just 1. So let's just make it -2. Yeah, this looks pretty good. I'll make it like that. Okay, so now we found, what did we find? We found that at 1, 1, it was a saddle point, and at -1, 1, it was a center. Yep, sure enough. There it is being a center. Now, if it gets far enough away, it stops just going into orbit, and instead it gets the little saddle point slingshot going on over here. But together, you make this nice little fishy picture. So we got a saddle point, and we have a center, exactly where the Jacobian told us they would be. Okay, so that was example C. Once again, confirmed. All right, now let's try example D. So that was xy, and here you have to do x times y, otherwise it thinks you're using a variable called xy. And then x minus 2y. And our findings here were 2, 1, and -2, -1 for our values. So let's say -4 to 4. So we have our x coordinates clearly in there. And let's just say -3 to 3 to get a good picture. Okay, and to remind you what we found, at 2, 1, that'll be the one up here, we found a saddle point. Yep. Sure enough. And down here, we found a spiral sink. Confirmed. It is definitely spiraling into that point, and it is definitely doing saddle point behavior around the other one. So once again, we have confirmation. As we predicted, we have it slingshotting around at the saddle point at +2, +1, and spiraling inward at -2, -1. All right, and for the final one, the predator, or not predator prey, the competing species model, that's going to be x times 1 minus x minus 1/3 xy. For the x. And then for the y, all very similar, just y times 1 minus y to begin with, minus 1/3 times x times y. All right, and here all of our action really is in the first quadrant, but let's go with -1 to 4 for the x, just to give us a little bit of context, and -1 to 4 for the y. Since these equations are totally symmetrical with respect to x and y, it's nice to give a little bit on both sides, even if the negative values don't necessarily make sense in the context of our specific example here. All right, so what we found here was at the origin, a star point. And what that means is it's a proper, so it's a proper source, and that means everything comes out of it pretty much even-handedly because we had a repeated positive eigenvalue. And sure enough, that's what seems to be happening. Once again, as far as the populations of animals are concerned, don't take too seriously the ones that are not in quadrant one, but the other ones, the ones that are in quadrant one, are meaningful. All right, and then at 0, 1 and at 1, 0, in both cases, we were supposed to have saddle points. Sure enough, there they are. And then at 3/4, 3/4, we were supposed to have a sink. And sure enough, there they are. All of the trajectories here are heading straight for that point. And so once again, technology has confirmed what we classified by using the Jacobian. All right, and just as a note, this is what the spiral points look like. Let me zoom in a little bit on that. Or not spiral points, I mean star points. So everything is coming out of the origin pretty much directly. And that's what happens when you have a repeated eigenvalue, but which is nonetheless complete. So here we have confirmation of everything that we thought would be true based on our analysis. All right, so what we have basically been doing here is taking this system or any of these systems, which are not themselves linear and therefore not themselves subject to the sort of analysis that we've been doing with eigenvalues and such. And we have found an approximation of those same systems which would be amenable to the same processes we've been using. And that linearization is a common technique that's used in math. When you're dealing with nonlinear scenarios, you can at least locally approximate them by linear scenarios. And that's what, in a lot of ways, taking a derivative is actually all about. And in the case of multivariable calculus, you have to take partial derivatives with respect individually of each of the variables. So that is that. All right, well, thank you for joining me for this episode of Math 256. Join me next time when we will be venturing into new techniques, new frontiers, new material, new chapter, something completely different from what we've been doing already. So stay tuned for that. Till then, bye.